Okay, so let's consider this interesting volume problem. Take a minute and pause the video, try it on your own, and then come back, and then we'll restart. So what I found difficult about this was just trying to draw a picture of it. So you have a sphere of radius 2 that's centered at the origin. Uh, you can just, the equation of the spheres are pretty easy. It's always x squared plus y squared plus z squared equals the radius squared. In our case, it would be 2 squared or 4. And I know what that looks like. We've got to stay above the xy plane, so that means it's like the upper hemisphere. But below this cone, z equals the square root of x squared plus y squared. So I drew both of those things, and I got this. So what you can kind of tell is you want to stay under the red cone, but above the blue circle there. That is the, we'll say, the equator of the hemisphere. Okay, and so we have some equations of these things. Like I said, the equation of that sphere is x squared plus y squared plus z squared equals 4. That's sort of nice because we know we're going to be starting from the origin and heading out to the surface of the sphere. So we can say that rho in spherical coordinates would always be between 0 and 2. You have two more things to worry about. You got to worry about the angle theta. But theta, we're going to do a complete rotation to get the whole upper hemisphere. So it's going to be 0 to 2 pi. And then we've got the angle phi. Don't forget the angle phi is the angle down from the vertical axis. So that's angle phi there. So you just need to remember one special thing about that cone. The cone y equals the square root of x squared plus y squared makes a 45-degree angle with the x or y axis. So I'll try and trace it over here in yellow. That yellow angle is 45 degrees. Now, if you're not sure why, consider for a minute if y were 0, you would have y equals the square root of x squared, which is y equals the absolute value of x. Well, that graph, we know, is comprised of two lines that make 45-degree angles with the origin. If we want, with the x-axis that is, if we want phi to make it down to the y-axis or the x-axis, either way, phi would have to be pi over 2 radians. So that gives us a boundary for phi now. Phi has to be bigger than pi over 4 to get down to the cone, and has to be less than pi over 2. And then finally, we know that a triple integral that gives us volume is just a triple integral of 1 dv. All right, so now we're ready. We're going to take those limits of integration and build this triple integral. So let's do that. So here we go. We've got the integral from, oops, that doesn't look so good. We've got the integral from pi over 4 to pi over 2. So that means I'm doing d phi last. Then we have integral 0 to 2 pi. I'm doing d theta second to last. And then I have the integral from 0 to 2, because that's the radius for a sphere, of 1. So that means I'm doing d rho first. And just don't forget you need a rho squared sine phi, because that's your correction factor for spherical coordinates. Okay, let's work on these antiderivatives one at a time. So this first antiderivative, rho is the variable. So the antiderivative rho squared is rho cubed over 3 sine phi, evaluated from 0 to 2. So we're going to be plugging 2 and 0 into that rho. So we take 2 and plug it in here, we get 8/3 times sine of phi. If we plug 0 into that rho, we'll get 0. So it'll be minus 0. So literally you just get 8/3 sine phi. Let's do the next integral, which is this one, 0 to 2 pi d theta. So let's do that. So this is 0 to 2 pi d theta. That's surprisingly nice because if theta is the variable, 8/3 sine phi is a constant with respect to that. So this whole antiderivative here just becomes 8/3 sine phi times theta from 0 to 2 pi. Plugging 2 pi in, we'll just multiply 8/3 sine phi by 2 pi. So I'll have 2 pi times 8/3 sine phi. And plugging 0 in, well, if I put 0 here, then I'm going to be subtracting nothing again. So now I'm left with the final antiderivative, which is going to be d phi. And I'm going to go from pi over 4 to pi over 2. Now, if you want, you might as well take those constants out of there. So for example, these two things together make a constant of 16 pi over 3. So I'm going to leave that outside my integral. And it's integral pi over 4 to pi over 2 sine phi d phi. And moving right along, we take the antiderivative, so we get negative cosine phi, evaluated from pi over 4 to pi over 2. So we do the cosine, well, let's just do it in pieces. So you have negative cosine pi over 2 minus negative cosine pi over 4. Well, cosine pi over 2 is 0, so that's gone. This minus and negative becomes plus. The cosine of pi over 4 is rad 2 over 2, so this whole thing is rad 2 over 2. Don't forget this constant up here, 16 pi over 3. So we end up with 16 pi over 3 times rad 2 over 2, or 8 pi over 3 times square root of 2. Okay, thanks for watching.